Today we are going to talk about syntactic sugar in D, also known as high-level properties. Syntactic sugar is a way to express high-level ideas rather than getting down into low-level operations. When people propose new features for D, most of the time they are syntactic sugar, not low-level features. Syntactic sugar is meant to save programmer time, make your code more readable, certainly it's to eliminate less bugs, and automatically take care of error-prone, annoying, tedious boilerplate. But of course there's a problem. There's always a problem. After all, if there wasn't a problem, there would be nothing to talk about. Most language specifications describe what the sugar does from a high-level perspective, but I never really understand things from a high-level specification of what they do. I'm not comfortable unless I know what exactly is happening under the hood. For example, when I read Bjarne Stroustrup's book on C++ back in the 80s, he kept talking about virtual functions in the book and what they did, and it all made no sense to me until I ran the code through his C++ translator, which translated C++ to C, and I could see what the generated C was, and then it was like, oh, I get it. I get what virtual functions are. I know how they work now. The point to understanding sugar is the point in understanding any kind of machinery that you use. You can make informed trade-offs about using it. You understand when to use it, when not to use it. You can build a subtle mental model of it. And on a more specific note, a lot of people have difficulty understanding how the scope and ref attributes work with higher level constructs, and by knowing how those higher level constructs are implemented, it'll be much easier for you to see how scope and ref fit into it. Well, we can start with C, because everybody knows C, and C is famous for having almost no syntactic sugar. Its constructs almost directly translate into machine code. It's kind of like that of a steam locomotive, because most of the machinery on a steam locomotive is on the outside where you can see it work, and it's fun watching it work, which of course is why I like steam locomotives, because it's fun looking at the machinery actually doing the work. C's syntactic sugar consists of values, pointers, functions, and structs, and that's really about it. It doesn't have much more than that. Let's start with something simple. The ref attribute. Here we have a struct, which has one field, A, and we have a function called get, which takes a reference to a struct S and returns the A field of that struct. And what it gets translated into is the ref gets translated into a pointer, and when we use the pointer to the instance of the struct, we indirect it with the star and retrieve the A reference. But if you're a suspicious person like I am, is Walter telling the truth? Are they really the same? So the compiler has some built-in features we can use to investigate that and see if they really are the same or not. The first such feature is the --b switch, which will print out the AST in an expression-like form for each function that is being compiled. And for the two functions being compiled here, you can see that it produces exactly the same AST output. Of course, sometimes you need a little bit more information, like what are the types attached to those nodes. And with the --b --f switch, it will dump the ASTs annotated with the type of each node. And you can see that, yes, indeed, the exact same tree is being generated. But we can go even further than that. And with the -vsm switch, we can look at the generated machine code for those functions and see, yes, again, it's generating exactly the same machine code for each of those two functions. Moving on to a more complex example is the dynamic array. it's not just a pointer, it's not just an array, it's a pair, a pointer and length, where the pointer is the pointer to the first element in the array and the length is the number of elements in the array. So if we have a function called add, which adds the first two elements of an array, it is rewritten in terms of a pointer and a length. So instead of the dynamic array being passed, it's split up into two values which are passed, the pointer and the length. And then the summation is the star p plus 1. Now I did mention array bounds checking before. Array bounds checking is not shown in this example to make it a little simpler to see what's happening. Out parameters are very much like ref parameters. The parameter itself is, like ref parameters, replaced with a pointer parameter, and then at the beginning of the function, through the pointer is assigned the initial value that is suitable for the type of the argument. So an out parameter will serve to both initialize the parameter and then allow you to return a value through it. Now things are getting more complicated. Struct member functions. If you're like me, the first time you set eyes on a struct member function, you would see that A is being set to I. Well, how does the member function get a value of A, or how's it able to set the value of A because A is not a parameter? Well, the trick is the compiler inserts a hidden parameter, we'll call it this, and that parameter is a pointer to the corresponding instance of struct S. And so we pass this in as a pointer, and then we can set A indirectly through this pointer. And when we call a member function, where here we get the instance of S and we call the member function set on it, we'll see the address of the S is passed to initialize this pointer, and of course the value for I is 3. Functions are similar but have another step up in complexity. Here we are also passing in a this pointer and using it to set the value A, and when we call it, we don't call the set function directly. We call it by accessing the vPointer member, which is a table of function pointers, and we index it to find the function pointer to the corresponding set function and call it, and then we pass it the pointer to the instance and the number 3. And this is how virtual functions work. They do not call their member functions directly. They call them through a table of pointers to functions. And this is what I did not understand with C++ virtual functions. I'd never heard of it. And when I saw the machinery of how it worked, it all suddenly became obvious how this all worked. Table looks like this. The first entry is a pointer to the runtime type information for the class, and then the rest of the entries are the addresses of the member functions. Nested function is a third kind of function with hidden parameters, and here we have a nested function inside org, and it needs to reference both I and j, which are not local variables of the nested function, but they are member variables of the enclosing function org. So how is this accomplished? What happens is the nested function again gets a hidden parameter, we'll call it p, which is a pointer to the stack frame of the enclosing function. So the parameter I can be addressed at offset 0 from the pointer, and the parameter j can be accessed by offsetting p by 1. And this is how it works. And when we call the function, we pass it the address of the parameter I. Now, you can do this in C, but because the layout of the local variables of a function is not specified and can change depending on compiler switches, trying to do this yourself is kind of a disaster in C, and pretty much nobody does it because of these problems. This is one case where having syntactic sugar help out is really a big improvement. What is a delegate? A delegate, like the dynamic arrays we had earlier, consists of two fields. One is a pointer, which we call a context pointer, and the other is the func pointer, which is a pointer to the function that implements the delegate. A struct delegate looks like this. We have our same old struct s, which we're very familiar with now. And in this function, bym, we want to create a delegate, and we need two things to form the delegate. We need the pointer to the context and a pointer to the function. So address of s, it gets set to the pointer member, and set turns into the address of the set to set the function pointer. Delegate is almost the same, but as is usual with classes, there's a step up in complexity. Everything is the same except the address of the function. Now the address of the function is set by accessing the pointer to that function that is in the vtable, and the vtable is accessed through the vpointer member of the class C. And the next kind of delegate is the nested function delegate. And so here we have our function org again, and our nested function, which has its own parameter z, and then it's accessing the parameters I and j from its enclosing function. We form the delegate by taking the address of the nested function, and the address of the nested function goes into to set the func pointer field, and the context pointer is set to the address of I, which is the address of the enclosing function's stack frame. Those of you who haven't fallen asleep yet have undoubtedly noticed that the three types of delegates, struct delegate, class delegate, and nested function delegate, are all exactly the same type. Once they are formed, they are indistinguishable from each other. This means they are interchangeable. One function accepting a delegate will be able to accept a delegate from a struct, a class, or a nested function. It will not be able to tell the difference because there is no difference between them. This is a particularly nice feature of D. A somewhat more obscure feature of D is the lazy function. In a lazy function, an argument is not executed when the function is called. It is executed when the function actually tries to, or when it needs a value from it. So here, our lazy int x, what it is it becomes a delegate. And the argument that it is called by, the ++ I, gets turned into a delegate. And you see this down at the bottom here, where the delegate is a lambda function. And the lambda function gets passed as a delegate to the FID function, which calls the lambda function whenever it's referenced and increments it by 1. So really, lazy function parameters are just syntactic sugar for a lambda function and a delegate. Statements are a fairly simple device, but save you a lot of time and can make code a lot cleaner. Version of the scope is the scope exit, which means that regardless of how the body exits, whether normally or through an exception, the code is going to be executed. So this diagram here shows the pieces of the syntactic sugar and where they get inserted into the code that replaces it, and you can see that it turns into a try finally piece of code. Failure is a little more complicated in that we want to execute code only if the body throws an exception. And so we see the lowered code is a little more complicated. We have some boilerplate in here. We need a try-catch statement. We need to add the exception and be able to rethrow the exception. This is even more complicated. Here, the code is executed only upon successful completion of the body. So this involves creating a try-catch finally statement with an extra flag, which tells it if the body successfully exited or not. So we know when to execute the code in the finally statement. And if you just looked at this try-catch finally, it takes you a while to figure out what is actually happening here. Whereas if you look at the scope success, it's very obvious what is happening. So this is exactly why you want to have syntactic sugar. You want to make complicated code look simple. It was Andrei Alexandrescu who convinced me that the compiler should be implemented in terms of rewriting complicated syntactic sugar into simpler constructs. And the very first one I did was the while loop. The while loop used to have its own pieces of code to implement it throughout the compiler. And the rewrite was to take the while loop and rewrite it in terms of a for loop. And it does that very early in the semantic processing, so that there's actually very little semantic processing for a while loop. It eagerly converts it to a for loop, and then it's done with it. So the compiler code only has to get the for loop right, and then automatically the while loop is going to be correct as well. So things like this are really a nice improvement. And we can see here how a Foreach over a range of values is rewritten into a for loop. And with the Foreach loop, you can look at it and instantly see what it's doing. With the for loop, you have to stop and think and look at it a bit. So here's another example of what some nice syntactic sugar looks like. Foreach over a dynamic array. All we really care about with looping over the array is being able to look at each element of it. So C is the element, A is the array, and body is the code, the loop body that's going to be executed. And you can see how it's rewritten into a for loop. And it's really pretty clear that the for each is a much nicer way to do it. And the rewrite is pretty simple. Sometimes when we're doing a for each, we still want to know the index into an array of what we're dealing with. So we just add the extra parameter j to the beginning of the for each, and you can see where the j appears multiple times in the boilerplate expansion. And isn't it nice that you don't have to type that boilerplate yourself and potentially get it wrong? Compiler does it for you, and it's much nicer. But in the end, it's just yet another straightforward for loop. Of for each loop is that you might want to do is you may want to modify elements of the array, and if you do, you put ref in front of it, which it just translates into the same for loop, except it puts a ref in front of the declaration of C. Now, D doesn't allow at the user level to declare local variables as ref. But internally, the compiler is allowed to declare its own variables as refs. So in effect, we're cheating just a little bit here by doing things that isn't available to the user. Reach over a range, and you'll see it produces quite a bit of boilerplate that, again, isn't always easy to suss out what this for loop is doing, but it's trivial to see what the for each is doing. Now, the neat thing is if you'll notice, the for each is exactly the same syntax as for each over a dynamic array. By having the same syntax, you can write generic code and have it work with multiple different types, and refactoring your code becomes easy instead of having to rewrite your for loops. Putting syntactic sugar is useful in a language if it is heavily used. And if additional semantics can be layered over it, such as safety, syntactic sugar is less prone to errors, it's easier to refactor, it's easier to encapsulate, and it usually just looks better. Belongs in the library. The advantage of library syntactic code sugar is it can be improved without needing to make expensive and disruptive changes to the compiler, and these things always take a fair amount of time to implement and vet in the compiler. Users don't have to wait, they can create their own. For example, the earlier Bitfield library implementation was done as a library function, and later on, because of the more convenient syntax, and that could be done if the syntactic sugar was added and for exact C compatibility, it was built into the language. Like anything else, you can overdo it and get that awful sugar high. Too much syntactic sugar, the language becomes big, unmanageable, a bloated mess. Often less can be more. And the goal and the job of the language designers is to pick just the right amount. You don't want your cocoa to be too sweet or not sweet enough. There is just the right amount of sugar to put into it. Future sugar to be added to C that we're thinking about and discussing on the news groups are sum types, pattern matching, and tuples, and they hopefully will be very nice additions and very useful bits of syntactic sugar added to D. There we have it. I hope you enjoyed this presentation. I hope you find it useful, and I hope you learned something, and come visit us over at dlang.org in the forums, and there's my Twitter handle. Goodbye.